Bismillahirrahmanirrahim. In this series of tutorials, we would be learning together that how to use ANSYS Fluent to find out the thermal comfort for a 3D model for a building, and this is the kind of results we intend to get after doing all the works. This is going to be the final. Okay, this video is very fast, so you won't be able to see. I need to slow it down in some other. Actually, what it shows is that it shows the air streams, and this ball actually revolves around, showing that how air is being circulated. So these are actually our two models we are comparing in this tutorial. One is a closed plan. As you can see, it is partitioned off right here, and then there is a open plan in which there is no partition, and we need to simulate all the conditions, the velocity, air velocity, and the temperatures and the sunlight in ANSYS in order to find which one is more thermally comfortable. First thing first, you would be needing a detailed AutoCAD drawing in order to start. So let's go to that. So here it is. As I said, one is an open plan. So this is the open plan, same four working desks, same 4 chairs on all working desks, and same capacity of air conditioners, cassette type air conditioners installed in on the same place in the open plan, and it is similar in the closed plan. The stark difference that would be that in open plan there is only one indoor access, the door, whereas in the closed plan there are 4 different doors. So that's the difference. If we view their section plans, you would also come to see that there isn't much difference over here. The only difference being is this partition, the full heighted partition. So now that we have understood the problem and we know what we are going to target, we would start the same thing in ANSYS, and I would be using ANSYS 17 for this tutorials. And the reason to use ANSYS 17 is that there is a third-party tool to get the thermal comfort contours over here, like so these are thermal comfort parameters: predictive mean vote and percentage of people dissatisfied. And this is not the usual contour you can get from ANSYS. So a third-party tool is used to solve to use the solution of this whole domain and then convert into these contours and get the data that now, okay, so this is the closed plan, open up, and it is somewhere around 0.936 on predictive mean vote scale. So it is close to 1. So it is a bit hot, but not that much. The HT standard sets the range at 0.5 to minus 0.5, so it is there. So without further ado, let's start with ANSYS. Okay, in ANSYS, as I said, I am using ANSYS 17, and it has a third-party tool which gives the contours in predictive mean vote and percentage of people dissatisfied, or should I say thermal comfort indices. So this over here is the geometry. This is the Fluent. The workbench, it contains, if you can see on the toolbox over here, it contains many models, many software packages to solve different set of problems. So if you have some sort of If you want to do analysis regarding some beam bending problem, you would be going for a different software package. Since we are dealing with simulations, comparative computational fluid dynamics, we would be going with Fluent. And once you have clicked Fluent from here, which should be over here, yeah, fluid flow. So such two boxes would open up, and actually one box would show up, and they right now they don't have any data. You can see the question marks. There is no setup, there is no solution, and naturally there is no result. There is a geometry with that I have imported, but I would be detailing that how to make that geometry. One thing I have said earlier, that you do need detailed AutoCAD drawings to make a geometry. So let's open up the closed plan geometry and see what's in there and how it was made. It's already there, but we would be retracing the steps at how it was made. Okay, so it's opened up. Yeah, so this is the closed plan. It's on the same dimension as it was for the as it was in the drawings. It's in the same units. And one addition I have made over here is that I have added this human model, a simplified human model, for reference and understanding. It doesn't play much part in our simulation results, because that is being done by a third-party tool, but it's a good practice to have a human model in 3D models. It immediately gives you the scale of the 3D model, because we daily perceive human body sizes, so we are very well are very well known that how much bigger a person could be, and in relevance to that you can find out what is the size. So how I started making this, that's actually okay. Let's pause here. Okay, as I said, we would be retracing our steps. So the overall area for this closed plan was, the overall dimensions were, I need to on the ortho, they were like 2060, and that's in millimeters, actually centimeters, my apologies, and 610. So what I did, I made a 2100 centimeter by 650 centimeter block, and let's actually see, a rectangle, and let's actually see that. So the dimensions are showing up here, and then I simply extruded it to 15 centimeter to make the base of the model. Let's unpress it. So that was the earlier, that was the base of my model. On this, the whole room now further we built. After that, I introduced a plane. This was the plane. I set its dimension over here, and then I made another sketch on the same elevated base. So let's look at that. And they were like of the same thickness as thick the walls are. So once that was there, it was extruded to 315 centimeters, and we can see why it was 315 centimeters, because yeah, this finished floor level to this ceiling level, that is 315 centimeters, so that's why it was extruded that much. And I got the boundaries. After that was the step of making the tables. Okay, in CFD you have to simplify things. You cannot go with the fancy designs. That would make your calculations much difficult later on. So that's what I did. I made the design very simple. Simply made some sketches and then extruded them to their height. I had the data from the detailed drawing. Now I would be then four other blocks around these four tables were made, so 16 in total, and they were later converted into chairs. If you could look at that. Okay, so now in order to make the resting place of the chair, one place where the stand or the support of the chair, the lumbar support, I had to do modeling for each 16 chairs individually. So let's actually make them appear in one go. So now you are seeing that the bases are showing up and there are still some to go. So let's go with that. Okay, I've again suppressed them. What I needed to do was to unsuppress them. I have to go one by one. There are limitations to using the 3D modeler of ANSYS. It's not as comfortable as other tools might be, SolidWorks or Creo Pro, whichever you are comfortable in. And there are ways to import the 3D models into this in Fluent. But what happens mostly is that those geometries often get distorted while importing procedures, and they often have small cracks in between them, and they do not give good results. So in order to get good results, CFD results, it's my personal practice that I do not import any geometry. I make the geometry, I make the 3D model within the ANSYS design modeler tool. So that allows me better results later on. But yeah, it's kind of a hassle. It takes its time. But that's a trade we have to make. Okay, all are opened up. So yeah, after that there were these cabinets, and again they were made on the floor plan. A plane was made on floor, and actually I would be making a separate tutorial on how to make a plane, and I would be making a simplified geometry for your proposal later on. But for timing, I am just retracing my steps that how I did that. Okay, that's roof. If I unsuppress that, the whole building would be covered, so let's keep it suppressed. Then these were the partitions. One thing you need to be careful about the partition is that you cannot allow these partitions to go all the way up. Although in the problem it is like that, and in many other problems you would be modeling, it would be like that the partitions, they go all the way up. But if you make them in such a case, while you would be doing the volume extract function, which we would be doing subsequently, it would make it 4 different entities. It won't consider it one body. It would consider it 4 different entities, and then CFD simulations won't be possible. So for partitions, just leave a little bit of space. Don't make it go all the way up. Leave 1 millimeter space in between the roof and let me explain it over here. Yeah. So if you are making the partition, I think you can just stop somewhere over here. Don't extend it throughout the roof. This won't allow much of the air to pass through, but it would make your volume extract function very easier. Otherwise, the volume extract would just make it four different bodies and you won't be able to proceed with CFD simulation. I would be detailing this in a subsequent tutorial later on, but for timing, this is just accept it as it is. Okay, so yeah, the roof is done. Then okay, let's unsuppress everything. So with the exception of roof, there were also the model which I used for CFD simulation. These simulations are already done. This is just now the tutorial. The model I used also had AC units, and I would be explaining in another tutorial, the second tutorial I would be making on geometries, that how to make cassette type AC units. It's not showing up over here. I have retrieved this old file, so I don't know why it's not showing up over here, but it's there in the actual model, so no worries there. So that's how you would be making 3D model, and that's how you would be interacting with this tool. Once you have made it, make sure you save it and save the project by a unique name every time. After achieving every milestone, it is a very good practice to save it. Let me show you my own files which I was working on. So my apologies, it's been a while, I have totally forgotten. Yeah, CFD workbench till geometry was final after the space claim. Closed plan solution with P1 model and 100 iterations. Closed plan done final 19th October 2025. So at every major milestone, at every major achievement, I have made a separate workbench file, so that I have if I lose the files, or if the system crashes, or if solution explodes, I do have a place from where I can retrace my steps. So that's a good practice. I would recommend you the same. And this was the first tutorial. In the same tutorial, I would also be, I think it would be good to open up the open plan too. And so let's actually open up the second geometry too and see say that for some. Okay, so this is the open plan. You can see there are no walls in between, and over here the AC units are showing up. In the simulations it is there, but for the purpose of tutorials I have retrieved old files, so it wasn't there. But I don't be worried, that I would be showing you that how to make these AC units. It's very simple. It's actually just sketching it up on yeah, here it is, sketching it up on a plane and then extruding it. It's nothing fancy over here. Yeah, so these were four dimensions. These were the four squares. As I said earlier, we do very simplified geometries in the CFD modeling. We don't make things complex, even if they are complex in real life. The typical example would be that this human body. Now this is a very simplified version. The same goes for the AC units. They were made and then they were further just extruded. Nothing fancy there. So with this, I conclude my tutorial. In the next tutorial, I would be going around how to make 3D model in Design Modeler of ANSYS, and we would be carrying on our discussion from there later on. Thank you so much, and do give me the feedback on if any other thing needs to be added to these tutorials.